system. I think they were also involved with some of the analysis at the Kodiak site. So John is here to enlighten us on some of the work that he's been doing. Thanks, John.
Thanks.
And where do I need to go? Okay. Thank you. All right. Like Ito said, my name is John Heeb. I'm here from Electric Power Systems. We're a company that's headquartered in Anchorage. I particularly work in the Redmond office in Washington, and I'm here to talk about the Kodiak System and some of the studies that we're currently going through with them. A little bit of background on EPS. We are, again, headquartered in Anchorage. We have a bunch of clients mainly in Hawaii and Alaska, and we kind of specialize in isolated systems. A little background on the Kodiak system. They have a 25 megawatt peak, can get down to 11 megawatts. Recently their board of directors voted that they wanted to get to 95% renewable energy by 2020, which is a doable goal. It will be a little bit difficult though. Right now, they are operating with 2 hydro turbines rated at 11.25 megawatts. These two generators provide about 80% of their yearly energy sales. In August of 2009, you guys finished installing 3 1.5 megawatt wind turbines on Pillar Mountain, and that has already reduced their energy from diesel from 20% to 11% of their yearly usage. And again, their goal is to get down to 5. Here's a quick picture of the existing installation. They've got those 3 1.5 megawatt turbines. So I guess you guys will be out going to see that on Sunday. It should be a good trip. So Kodiak approached us in EPS trying to get a handle on how much more wind they can take on their system without running into system impacts. Things we looked at were voltage ride-through issues and frequency regulation. Their system is set up in such a way that their hydro resource is a fair distance away from their load, so they do have a little bit of voltage issues on their system. But through our analysis, it didn't really turn out to be a huge issue. What we did spend most of our time looking at was the impact on their frequency regulation of adding this wind. So that's kind of what this discussion is going to be about today. First question we had to ask ourselves was, if they expand to 6 turbines, how much worse will their frequency regulation be starting from today? And particularly, what measures can we give to Kodiak to say, your frequency regulation is 5 now, if you add these, it'll be 6. So we need to give something that would make sense other than just eyeballing a plot, right? So one of the advantages that they have is, and foresight in Kodiak, was to make enough room for a 3rd hydro turbine at the current facility. So they have everything set up in case they want to add this 3rd turbine. So first thing we did set about when starting this study, we asked Kodiak to give us some of their data. Can you guys give us some SCADA data so we can actually see what your actual frequency looks like on a typical day? So they ended up giving us the the wind plant output in 1 second regulation, or 1 second time frame, and the hydro unit outputs every 2 seconds. So starting from there, we wanted to move forward and say, we want to benchmark your system to figure out, are our models accurate? So using that, we wanted to make sure that our hydro models, and they have a very unique hydro system in that they have these 2 hydro turbines with a very long tunnel system. And the effects of that can be pretty significant on the speed of the unit regulation. Here's exactly what I was talking about. So Kodiak, in preparation for these wind turbines, they went ahead and improved their governing systems on their hydro turbines so they can improve their response. But they do have this issue with this 20,000 foot long tunnel. So basically, if you open up your valves asking for more water, it's going to take time for that water to get to the turbines and actually supply that power. So that's one of our constraints that we're dealing with. So what we did in this study is we started with all the data that's provided from the generation side. We went ahead and kind of backed out what the system loads were, what the losses were for each time step. And then for the wind, since we already had the actual wind data, we used that as a kind of a direct injection, so kind of a negative load situation, just to verify that our hydro models are working correctly. And we use those to simulate what the frequency would be for these cases we had in mind. Oh, that's not showing up terribly well. But what we have up here is we have a plot showing the system load that we had calculated. It's going up and down. It's probably hard to see. And then we have our recordings of the here we go. We have the actual Terror Lake generation outputs right here, and as well as our wind variability, which you can kind of see is going up and down. And right here you get a peak of about 4 megawatts out of the 4.5 megawatt capacity, followed very shortly by a minimum of about 1 megawatt. So you are dealing with some decent variability in this particular 15-minute snapshot that we're providing. So based on our, thanks, Kat. Based on our simulation, this is really what we're trying to figure out, is are our models accurately representing the frequency that you see on your system? And the big things to keep to have a look at here are the magnitudes of the peaks and valleys of our frequency. And this scale is from 61 hertz to 59 hertz. So we thought we did really quite a good job of getting those models to match up with the peaks and valleys. So this was kind of the big thing for our study, was to get our models to accurately represent the system. From here, once we're confident with this, then we can move forward and say, hey, what happens if we add more wind? What happens if we add that third Terra turbine? So we're comfortable with our benchmark. Next thing is, how do we assign a metric so that we can say it's better or worse, other than just saying, look at the frequency, it's different. So what we did is we took some real basic statistical measures, some Gaussian distributions, just to say, here's what your today's system looks like, and here is what it would look like if you added another wind turbine. So here's a quick plot of what today's system's looking at, and basically the number we're looking for is just our standard deviation up there of 1.74. So this is their actual measured information. Our simulation came back with 0.145. So we'll use this 0.145 as our comparison for additional cases. All right, so starting from there, we said, okay, what's it going to look like if we go to 6 wind turbines, which is where Kodiak eventually wants to go, double their wind output to 9 megawatt capacity. And then to evaluate whether this third hydro turbine will be able to keep up with those additional wind resources. So here's a look at what that would look like as far as a frequency distribution. Originally we had that 0.145, and if we double the wind turbine, we actually end up getting 0.233. So essentially you're seeing about twice as much frequency variability. Not quite. And then here's what it would improve to if you add that third turbine to 0.176. Again, just numbers, but you can compare them as opposed to just kind of looking at a trace. So 0.176, higher than 0.145, so we're going to see worse frequency response. So with that, we went back to Kodiak, said, hey, guys, it's going to get worse. There you go. That's your study. And of course, the obvious next question is, well, how much can we get before we start seeing degradation in our frequency performance? Because they're currently operating what they feel comfortable with, but much more they're starting to run into some issues with their system. So we went back and did kind of a similar analysis. We did 4 and 5 wind turbines, all the same size again, and came up with our little table here. The red showing today's operations, and the very top one showing the best frequency regulation, very bottom showing the very worst. Kind of the number that we keep on looking at is that third standard deviation. That's kind of the, statistically speaking, that's when you encompass 99.7% of your measurement points. So you figure 99.7% of the time we're between 59.7 or 59.57 and 60.44 hertz. And that's kind of where you get a feel for where you're typically staying. So the end results are it's between 4 and 5 wind turbines that they can have on their system, and add this third hydro turbine and still maintain a similar frequency response to what they have today. So again, if they add that fourth wind turbine, add another hydro turbine, they will actually improve their system based on our studies. Whereas if they go on and add that fifth, they might see slightly worse frequency response. So then it becomes an issue of do they feel they can handle that additional frequency regulation. Currently we're going through some more iterations as far as what additional tweaks can we make to this proposed third hydro turbine to maybe further boost the performance to where they can get even a little bit more wind. Things like running or adding inertia to that third turbine so that it might have additional mass. Maybe that'll help their frequency regulation. Also, playing around with the needle valve opening times, maybe get quicker response out of their hydros. But again, that might be very well limited by that very long tunnel. So it's a work in progress, and it's been a pleasure working with the guys from Kodiak. They've been very helpful, and hopefully we can move forward and meet that 95%. That's it for me. Any questions?
In the modeling, you did not look at anything like flywheel storage as a sponge to take a little and help on those responses?
No, we didn't. This is kind of the first step of it. They have the powerhouse set up for this third turbine, so it's kind of the obvious first step to go look at that third turbine. As far as additional remediation steps like flywheels, that's kind of what we're looking at now as the next step of
And
solutions.
The third turbine uses the same common tunnel.
Yes.
So that's the constraint as well.
Mm-hmm. Exactly.
Yeah. So is there any pondage with the hydro, or is it strictly run a river? And can you characterize what the response time is for the hydro?
Yeah. I guess Darren could probably answer the first question. He knows, and I'll take the second one. The response time, you're looking at about. You do see some response out of the units within a few seconds. However, the issue is you do run into some instability issues, particularly system oscillations when you start moving up and down. You want to you open your needles, you want more water, and then a pressure transient goes back to the lake and comes back down and hits the turbines, and then you go too far over frequency, and you can get a ringing. So that's a constraint with the tuning of the governors, certainly.
So what are the issues with your frequency moving around? It doesn't look like it's moving around that much. What's the big deal?
The issues there are has to do with customer expectations. One of and Darren could probably speak to this. One of your main customers is the military, right? Yeah, and so they'll have. I'm sure you guys have constraints as far as expectations on frequency.
Then also, what you've got is 99.7% of the time it's all fine, 0.3% of the time it's not, and if that takes your system down, it's not very good. So our expectations are to stay with what we're in now. We can keep the lights on. We've had no load showed events with the turbines in their current configuration, so we're not going to get worse than that.
It doesn't look like it's going to take your system down, though, does it? If you had the fifth turbine.
We had the fifth. No, it looks like we should be able to. It's just going to get marginally a little bit worse. So we probably could, with a 3 hydro, 5 wind, we probably could be about where we are today. But we'd like to see if we can maximize the potential push to 6. And with that, though, 6 turbines with this curve, we'd have some lights going off then.
You think your system would be unstable with 6 turbines?
Well, from that metric, 0.176 to 0.145, you'd be 20% worse than you are today. We would end up with load shed events throughout the year.
How often? And how significant? I mean, what's the trade-off there to go into 6? I mean, maybe you want to go there.
From a standpoint of planning on load shed events to keep for renewable energy, I don't think that's a good trade. I mean, we're probably going to have a few every now and then anyway, but planning on load shed events, we couldn't do that. Whether it's the Coast Guard we're going to serve or the processors or whatever it may be, if those hit at the wrong time, they could be pretty damaging to our customer base.
How many kilowatts are you talking about, or what is the load to make the frequency change here? What is your?
Well, I guess let me step back here. Oh. Maybe show a trace here. It's going a little too fast here. Okay, so I guess if we're looking here. First of all, let's find our worst frequency spot, which should probably be about this 180 to 270 second. We got a frequency spike there that gets down to, so this gets down to 59, a little bit below 59.6 hertz. What we can see here is we have this coupling of the loss of about a megawatt, and then we've got about 2 megawatts here. So we're looking at about a megawatt swing in that time frame that causes that 0.4 hertz difference. And that's a swing in the wind output and the load combined. So you can get decent sized swings. And that just has to do with the response rate of the hydros. This is a case when they didn't have any diesels on at the time. But does that answer your question?
Yeah, thank
Okay.
you. That's very good.
For the wind output, as you expand to 6 turbines, did you guys look at or consider at all the effect of the additional geographical spread of the turbines and whether that would have any impact?
I knew that question was coming. No, we didn't. The assumption there is that yes, with the added turbines, you will probably get some benefit of the geographic distribution. However, this being an initial study, we wanted to assume a conservative standpoint, assume that our variability is going to double. So it's very possible that some of our results could be overly conservative. Good question, thank you.
What software do you use for analysis?
This analysis, we actually ran PSSE transient stability models, and we ran them for this 15-minute time frame.